Hello everyone, this is Varsha. I'm currently pursuing my BE in 5th SEM CSE AI department in Sri Venkateswara College of Engineering. In this session, we will discuss about an undecidable problem, that is RE. Let us see what is undecidable problem. Undecidable problems are computational problems for which there is no algorithmic procedure to determine a correct answer for all possible inputs. In other words, we cannot determine the answer correctly, or there is no general method or algorithm that can decide whether the given instance of problem is true or false for all convincible outputs. One of the most famous examples of an undecidable problem is the halting problem. Here are some key points about undecidable problems in ATC. First one, no universal algorithm. Undecidability implies the absence of a universal algorithm that can provide a correct answer for every instance of the problem. Next, Turing machines and computability. The concept of Turing machine is often used to reason about computability. If a problem is undecidable, it means there is no Turing machine that can algorithm for all cases. Next, let us go with the proof by proof by diagonalization. Many undecidability proofs involve clear techniques like diagonalization, where the assumption of existence of a decision procedure is used to construct a case that contradicts the assumed procedure. Next, implications for formal system. Undecidability results have significant implication for formal systems and the limits of what can be effectively computed. They highlight the inherent incompleteness and limitations of certain types of computational processes. Next, reduction. Undecidability proofs often use reduction, showing that if there were an algorithm for solving one problem, it could be used to solve another known undecidable problem. Let us go with an example. In addition to the halting problem, other examples of undecidable problems include correspondence problem and certain problems related to formal languages. Now, let us go with the definition of RE. RE means recursively enumerable problems. RE stands for recursively enumerable. A recursively enumerable set or a language is a type of set or language for which there exists a Turing machine that can enumerate its elements, though not necessarily in a systematic or finite amount of time. Formally, a language L is recursively enumerable if there exists a Turing machine M such that for any string W in L, if you run M on output W, it will eventually halt and accept W. However, if W is not in L, M may either reject it or run indefinitely without halting. Let us see some of the key characteristics of recursively enumerable languages include enumeration property. There is a Turing machine that when given enough time can generate all strings belonging to the language. Halting behavior. The Turing machine may not halt for strings that do not belong to the language. Therefore, it does not necessarily provide a decision procedure for membership in the language. Next, let us see with the acceptance of positive instances. For strings that belongs to the language, the Turing machine will eventually halt. Now, let us go with the explanation of the concept of undecidability. The concept undecidability refers to problem that lack a systematic method to determine if a given input will satisfy a specific property or not. Implications. It challenges the limits of computational power and has profound consequences in algorithm design and artificial intelligence. Now, let us go with the overview of the problem in question. Complexity. Undecidable problems are often characterized by their intricate and convoluted nature. Unbounded shape. They have an unbounded number of possible instances, making the search for solution highly. Now, let us see what is halting problem. The halting problem is a classic and fundamental problem in the field of theoretical computer science, computability theory, and automata theory. It was introduced by Alan Turing in 1936 and is used to demonstrate the limits of what computers or any formal system of computation can achieve. The halting problem is defined as follows. Given a description of arbitrary computer program that is represented as a Turing machine and its input determine whether the program will eventually halt, that is, it will terminate or continue running indefinitely. In other words, can we design an algorithm that, given any program and its inputs, will decide whether the program will eventually stop or if the program run forever? Alan Turing proved that there is no general algorithm that can solve the halting problem for the all possible inputs. This result is known as halting problems undecidability. This is based on a clever use of self-reference and a technique called diagonalization. Now, let us see a brief overview of the proof. Assuming the existence of halting oracle. Suppose there exists a magical halting oracle that can determine whether any program halts on a given input. Now we should construct a contradiction. Using the halting oracle to construct a new program that contradicts its own existence, this is achieved through a process called diagonalization, where the new program does the opposite of what the halting oracle predicts. The contradiction. When we feed this new program to the assuming halting oracle, we reach a contradiction. If oracle says the program halts, then it doesn't, as per its own code. And if the oracle says the program runs forever, then it halts, again as per its own code. Conclusion. Since the existence of a halting oracle leads to a logical contradiction, we cannot we can say that there is no general algorithm to solve the halting problem for all the cases. Thank you.